Yeah. Yeah, in the last class, we have discussed about why we need to have the definitions of the power quality issues, and there are the different kind of the vocabulary or terminology is there for the different power quality issues based on the IEEE standard and then the IEC standard also. They have categorized it. Most of these are coming to the same I mean, technically, more or less, it is same only. Okay, same only. Okay, yeah, and we have seen like how they categorize in the IEEE standard, and we have seen like based on uh, the different attributes, they are categorized to steady state phenomena as well as the non-steady state phenomena, and yeah, in the last class I have discussed about the transients also. Okay, these are the transient or momentarily occurred in the system because of the passive elements of inductor and then the capacitor also. Okay, in the transients we have seen like there are oscillatory transients and then the impulsive transient also. There we have seen about the what is the impulsive transient also. Okay, which is a sudden non-power frequency change in the steady state condition of voltage or current, or the both also. The impulsive transient is a unidirectional, either it have the positive change or the negative change in terms of the magnitude. These are categorized based on the rise and the decay times, which can revealed by the spectral content also. Okay, the most common cause or the reason why the impulse transient is going to occur is the lightning phenomena. How we can suppress this the lightning or the impulse transient be by providing a surge arrestor or providing a low impedance path in order to drop out the energy also. Okay, basically the surge arrestors are being used in to suppress the impulsive transient. Okay, the issues which are going to occur because of the impulsive transient, if you allow the impulsive transient in a system, is there is a failures of I mean, it is going to fail the insulators. If there is a insulator failures, then we'll be having a dead shot, and then there is a chance of collapsing the entire the distribution system or the grid also. Okay, I mean, if it is there in the transmission level, the lightning is there. If it is there in the distribution system, it is not going to collapse the entire the grid, but it is going to cause an interruption once after the lightning phenomena occurred, and if lightning phenomena occurred, if there is no kind of a if there is no surge arresters, in that case it causes a fault in a system also. Okay, and we have seen one of the waveform of the impulsive transient is basically it is an order of a kiloamperes, around 24 kiloamperes, which is going to flow. It is in the only in the negative direction. Okay, yeah. Okay, and this one more point here. They are generally non-conducted far from the source or where they enter the power systems. In some cases, be conducted for quite some distance along the utility lines. Impulsive transient, it can excite the natural frequency of the power systems and produces the oscillatory transients. That is, it is sometimes the frequency which the impulse transient occurrence is something around, if it's I mean 10 times of the fundamental frequency or any, I mean, or else other 2 kilohertz also. The 2 kilohertz impulse transient may have a resonate with the system level frequency also. System have certain frequency component, certain LNC component also. The overall Thevenin's equivalent impedance if you consider, and it has some kind of a resonant frequency, some frequency is there. I mean, if the whatever the impulse transient frequency which is oscillating, if it is coinciding with the natural frequency of the power systems, in that case we will be having an oscillatory transients. Okay, the impulsive transients is yielding to an oscillatory transient if if the impulse transient can excite the natural frequency of the power system circuits. Okay, that's what the impulse transient is yielding to an oscillatory transient provided in the case of where it is frequency is meeting to the power system frequency or the system frequency also. Okay, the oscillatory transient is a non-sudden and non-power frequency change in the steady state condition of voltage or current, or both, that includes both positive and negative polarities. Okay. The oscillatory transient is basically occurred to the back-to-back capacitor energization, results in oscillatory transient currents in the order of tens of kilohertz. Okay, going to see the figure also. And then the cable switching, where cable switching is energizing the cables also. It is not just the cable connection or a distribution system or a transmission system also. We need to energize the cables also. In that case also we'll be having the oscillatory voltage transients. Okay, medium frequency transients can also be the result of a system response to an impulsive transient. See, in the oscillatory transient, when you see here over here in this particular table, we have in oscillatory transient, we have a medium frequency component, high frequency, and the low frequency. They have given the order of this frequency components also. And terms of the magnitude and type of the duration, the decay in the sense that reaching to a steady state from one steady state point to another steady state point. The oscillatory transient also, the impulsive transient also, in the medium frequency range, it is going to yield to an oscillatory transient. That's what here it says. Okay. Yeah, medium frequency transient can also be the result of a system response to an impulsive transient. System response to an impulsive transient. That's what the frequency which with the impulse transient is oscillating with the system frequency. In that case, the impulse transient is going to have is going to convert to an oscillatory transient. Okay, the oscillatory transient, if you see the waveform, it is going to look out this way. It is having the change both the positive value as well as the negative value. This particular waveform is caused the oscillatory transient current caused by the back-to-back capacitor switching. It is not with respect to the current and also with respect to the voltage also, or in the both also there is a chance of occurrence in a system, that is voltage and the current also. The oscillatory transient with the principal frequencies less than 300 Hz can also found on the distribution system. Okay, 300 Hz also. We can. It's not like that we will be, the occurrence is an order of the kilohertz, but we can have at 300 Hz also. We can have a oscillatory transients in the distribution system. And we have seen this particular point in the earlier, we have discussed it also. I'm just revealing one more time. These are generally associated with the ferroresonance and the transformer energizations. Okay. The ferroresonance is a phenomena which is of a nonlinear kind of a inductive properties, where the inductance is the behavior of maybe the core or maybe the applied voltage also. Okay, it is going to change the inductive reactance. Okay. And then the transformer energization also is also going to have this kind of the oscillatory transients also. Okay. Yeah. Coming back to the voltage imbalance, we have stopped over here also. Generally, the voltage imbalance, when you say about the voltage imbalance, uh, the basic or voltage imbalance or the unbalance in a system. The unbalance a system which we are going to study with respect to the by considering the symmetrical components. The symmetrical components in the sense that we are going to convert the unbalanced system to a positive sequence component, negative sequence component, and a zero sequence component. These are the systems which are balanced also, which are balanced. With that, what is the advantage which we are going to get is, you all know it also in your easy level. We are going to study or we are going to can do the analysis by considering a single phase system or a single line diagram also. Once you convert the three phase system into a three phase unbalanced to a balanced system. Uh, in finding out the voltage unbalance factor or the voltage imbalance factor, we can use the symmetrical components. With that also we can evaluate the voltage imbalance factor. The voltage imbalance with respect to symmetrical components is a negative sequence. Here in the third point, it is says, the third point it is given over here. Just a minute. The negative sequence or the zero sequence component with a positive sequence component can be used to specify the percentage unbalance. The percentage unbalance. What we do was we just convert over here. Yeah. What we do was we try to take the unbalanced voltages of VA and then VB and VC. We have the conversion factor of it is about 1 a square and 1 a square of A, where we just multiply with the unbalanced voltages, unbalanced phasor voltages of VA and VB and VC. We are going to get about a zero sequence and then the positive sequence and then the negative sequence. The voltage unbalance factor going to evaluate with respect to the 0 V0 or Vn by the Vp. This way we can going to calculate the voltage unbalance factor. But the unbalance, the unbalance or the imbalance can be there in the current also, or it can be there in the case of the, we can see that voltage in the voltage we can see, but it can be there in the current also. But in general, in the current also, we can make of use of this particular equation to find out the current unbalance factor also. There is another definition in literature. It is available in the literature. It is available. It says about the maximum deviation from the average of the three-phase voltages or the currents divided by the average of the three-phase voltages or the current. What we can do is we can find out the average voltage is of VA or the VB or the VC. As such, like they have not very specific about whether we need to take about the phasor or something else also. Okay, they have not given anything also. Okay, but try to figure out yourself like whether we need to cover for the phasor or else the only the magnitude. Or else the only the magnitude. You just explore it out how we can evaluate the average. Maybe I'm not sure about it. Whether we can take the only the magnitude wise. Once after finding out the average, how you find out the voltage unbalance factor is, there is a maximum deviation uh, maximum deviation of voltage of phase A or phase B or phase C with the average voltage with the average voltage by the V average. Okay, or else we can have to this maximum value of either VA or VB or VC with respect to the V average by the V average. This way we need to find out. This is can be applicable to the current also. As such, like these are the definitions which are available in the literature, but still people are continuing or are debating how to find out the voltage unbalance factor. In generally, the IEEE standard, they says about IEEE standard of 519. They give about this particular equation as well as this particular equation also. Either way, it is you can evaluate it also. Okay. But these are the things, the voltage unbalance or the current imbalance are going to occur. One thing is the uneven distribution of uneven distribution of a single phase load. Why this voltage unbalance is going to occur? Because in a three-phase system, we'll be in a three-phase system. The phase A, maybe the loaded of phase A maybe is loaded to something around 10 amperes, maybe of 20 degrees. Maybe the B phase maybe of 20 at an angle of minus 240 also. Sorry, okay, no problem. Maybe IC can be having around 40. This way you will be having a currents of also the unbalance. The loads which are being connected in a phase A and phase B are uneven, or the phase of the B is loaded much also. Okay, this once you allow this kind of the unbalance, what is the issue which is going to occur is because of the loads which are connected to a distribution system or the uneven connection of the loads will be creating a very serious problem, which is one of the problem is the neutral current. Once you have a neutral current, loads which are being connected, okay, this way of IA, IB, and IC, this particular, just a minute. Yeah, one thing is the neutral is loaded excessive. I mean, the current flowing through the neutral is excess current is going to flow. What is the problem which is going to occur when you allow the neutral when you allow the neutral current? Okay, might be you have studied about the problem which is there, the neutral shift in the voltage. Generally, with respect to the source neutral, there is a source which is there. If you measure between with respect to this and this, we were thinking that to maintain the zero voltage, generally the ideal condition. It is not so it is going to happen. Even still they are going to maintain the very 1 to 2 volts or even 5 volts. I'm not pretty sure about it. What is the typical voltage range to be maintained in the distribution level? Please try to explore. Even I'll try to get it from the internet also. This voltage, they says about it should not be exceeded more than this particular voltage. If it is exceeded, if the neutral voltage is going to shift because of the excess neutral current is flowing because of this particular nature of the uneven loads. Okay, nature of the uneven loads. Because of that, the neutral will be loaded much also. Because of that, we will be having the neutral voltage shift, and because of this reason also, this particular point at the terminal point, you will be getting about the unbalanced voltages of the phase A, and then the phase B, and then the phase C also. Okay, and then the phase A. Because of that, what will happen was, if there is any kind of an induction motor which is going to connect at this particular phase, a three-phase induction motor has been connected over here. In that case, what happened was, there is a circulating current which is going to produce because of the voltage unbalance, because of the terminal voltage unbalance. If we excite the induction motor, if you excite the induction machine with the unbalanced voltages, if you excite the induction motor, excite the induction motor with the unbalanced voltage, we say that we will be having a circulating currents. Apart from that, there is a pulsating torque which is going to occur. Okay, the pulsating torque is what we expect was, in the induction motor, we expect a smooth torque, a smooth running of operation also. We'll be getting a pulsating torque. The pulsating torque will be tear out if you be allowing the voltage unbalancing system. The bearings will be tearing out. That is also leading to a problem also. Okay, what is the main thing is, as we see that power quality definition says about it, we see that the system should have a satisfactory performance, what it has to be. But when you have the voltage unbalance, we are experiencing for an induction motor, for an induction motor application, a pulsating torque that is not being allowed in a system also. Okay, if it is a three-phase system, I have given an example for a case of a three-phase, a four-wire system. If it is a three-phase, three-wire system, if you have the voltage unbalance, in that case, we'll be having a circulating currents in this phases. If you don't have this particular fourth wire, then we have the circulating currents. That is not in a usual practice to be allowed a circulating current between the two phases. Okay. Yeah. Here the primary source for the voltage imbalance of less than 2% is single phase loads on a three-phase circuit. They have given some of the problems. The voltage imbalance can also be the result to blown out fuses in one of the phases of a three-phase capacitor bank. Okay, that is of a uneven charging of it also. Okay. The severe voltage imbalance greater than 5% can result from single phasing conditions. Okay, generally in a system, the allowed voltage unbalance factor is less than 3% only. Okay, less than 3% only. We were not going to allow the voltage unbalance more than the 3%. Okay, what here a severe voltage unbalance factor can result from a single phase condition only because of single phase loads only. Yeah. Next, we are going to see about the waveform distortion. This is a very important thing which we were going to look into the very serious power quality issues, and we are going to address, or we are going to study in detail, or not in detail, we are going to study one of the devices to suppress the waveform distortion, to suppress or to mitigate the waveform distortion. Okay. What about the voltage imbalance? I just want to know that the voltage imbalance is a steady state phenomena or a non-steady state phenomena. This is the voltage imbalance is a steady state phenomena. This is there for a whole day or a whole few number of cycles also. Okay. Yeah. Coming back to the waveform distortion. The waveform distortion is defined as a steady state deviation from an ideal sine wave of power frequencies. Okay, an ideal sine wave, if there is any deviation from a pure or the ideal sine wave of power frequency of the 50 hertz. And it is categorized, the waveform distortion is categorized based on the spectral content of the deviation. Spectral content of the deviation. These particular issues are the waveform distortion issues. Are going to occur primarily because of these attributes also, or these what to say, these quantities are creating the or deviating from the ideal sine wave. Suppose if you have a signal of a sine, if you have a signal of a sine waveform, okay, of a sine waveform, if you add any kind of a 3-volt signal for this, okay, I mean sudden voltage, what happened was we will be having a shift in this particular waveform also. Okay, we'll be having a shift in the waveform. Okay, do you think that these kind of a DC offset are the DC loads in an AC system? In an AC system, is there any kind of a DC loads, or is there any chance of occurrence of a DC offset in the voltage waveform or in the current waveform? Yes. What kind of the loads are creating the DC offset? Can anyone? What kind of the loads are creating a DC offset in a system? Are you there or?
Inductive loads, sir.
Pardon?
Inductive loads.
Okay.
Non-linear load.
Okay. 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 Alok Kumar, what is a non-linear load? Pardon?
So like MOSFET.
Okay. Okay. Fine. See, the MOSFET and all they can use in the DC converters also. Okay, in the DC converters or any other applications. Okay. Fine. I mean, you all know about one of the factor is the half-wave rectifier, right? Once you have a half-wave rectifier, that will be allowing a DC current. See, if you have at this particular point a diode which is of carrying a, okay, in that case the current which we have been expecting for this particular voltage of only the one of the signal only. Okay, it is kind of a DC only. It is kind of a DC, provided that if you use any kind of a filter over here, we can make out still a kind of an average current of this kind of nature. Okay, this kind of half-wave rectifier loads are creating a DC currents or a DC currents or the DC currents. Okay, that is creating a shift in the voltage, or even in the current also, or even in the current. Typically nowadays there are very less amount of the DC current is demanded by the loads. Generally, in an AC system, whatever the loads which are been there in day-to-day life also, they were not making out or using out this kind of any kind of a non-linear kind of a loads, any kind of non-linear loads of this kind of the nature. Okay. Very few amperes or if you take about 100 amperes of a loaded current, it's the order of a point, not 1 ampere or a point. When 0.1 ampere is also a huge current, but very few ampere or a milliampere of a current, a DC current requirement is there in the loads. Most of the loads are not. They're all using about the full wave rectifier loads. Full wave rectifier in the sense, like when you use a full wave rectifier, you can get in this particular AC side both the side also will be getting. If you use a full wave rectifier, we'll get a current of in this kind of the nature, but this side you get a current of a DC current.
Sir, your screen is not visible.
Just a minute. Sorry. I just stopped the sharing the screen also. Okay. Yeah. Once you use a full wave rectifier, we will get the current when you use a full wave rectifier over this case. We will get the current of this nature in this particular DC side. In AC side, what we experienced was we experience a nature of the current. Nature of the current is this kind of a nature of the current in AC side, but on the DC side, we get a current which is of this current in the DC side. I'm just reduce the magnitude because you will be knowing it. See, most of the loads, what they are going to use is they are going to use a full wave converter only, not the half wave converter or half wave rectifier also. Okay, because they are not going to have a DC currents in a system also. Yeah, one thing is the DC offset is one of the quantity which is creating the waveform distortion. Okay, next is the harmonics. The harmonics in the sense, like you all know about it, the power electronic devices which have been creating the harmonics. The harmonics are the integer multiple of the fundamental frequency. The harmonics are the integer multiple of the fundamental frequency. Okay, these are the maybe EFN type of things. These kind of the harmonics, which are majorly why the harmonics are going to exist is because of a nonlinear loads. The nonlinear loads. Okay, nonlinear loads are maybe the power electronic loads. Not the inductor and the capacitor also. The power electronic loads. And other loads where the impedance is changing with respect to the time. That means that Z of t is a variable with respect to the Z of t is dependent on the applied voltage V of t and also the function of the time. That means that if your Z of t, if we assume that it is a constant, this is a Z of t signal, Z of t, and this is a voltage signal. In that case, you expect a current, or when you have a Z of t and is not varying, then you expect with a scaling factor of the current, Scaling factor in the sense, like there is a recurrent, I of t is equal to maybe V of t by Z of t, maybe of this kind of a current waveform which we expected. Which we expected. But suppose I have given an example also in the last earlier lectures also, where When you take about a diode and when you take about this rectifier, I'm just giving an example over here. In this case, the Z of t during the positive cycle, if you take the Z of t, a voltage signal, and this particular signal, Z of c, I'm have taken here is a power electronic device only. It's not a other component. The Z of t is offered very low impedance during the positive cycle. During the negative cycle, it is offering the high impedance. Maybe it is order of even the high impedance. I just have given. It is offering the high impedance. Here Z of t, the impedance is a function of the applied voltage with respect to the time also. It is not necessary of a power electronic devices. Wherever the load is dependent on the applied voltage or with respect to the time t, in that case we can call it as a nonlinear load. A nonlinear load. Whereas in just now someone has pointed out as an inductance. The L is a nonlinear kind of a load. It is not. The impedance is same only. With respect to the time, the L is constant. The impedance is same only. Okay. The inductive reactance is same only, or the capacitive reactance is same only. Okay. Maybe basically the LED lamps are there, right? Maybe the incandescent lamps also. Some of the loads where the impedance is changing with respect to the time also. Okay. The nature of the current of the incandescent lamp is not a pure sinusoidal. It is also some kind of a nonlinear load because the impedance is changing with respect to the applied voltage also. Okay, here this graph which is showing it is the impedance of a diode. Positive cycle it is offering a very low impedance. The negative cycle it is offering the high impedance. Okay, that way we can say they have categorized as a nonlinear loads. The point is it's not necessary that to have the power electronic loads. Other loads where the impedance is changing are going to have the harmonics. Okay. Next is the interharmonics. These are the interharmonics which are here the waveform distortion says about is a steady state deviation from an ideal wave, right? We have seen like the DC offset is changing from the ideal sine waveform, or it creating the waveform distortion also, Suppose when you see that this particular graph, especially this particular graph, where we have seen like because of we have added the DC offset, right, in the voltage, then there is a shift over here, the DC that is also is deviating. The DC offset also is deviating from the ideal sine waveform. Whereas if you are creating the harmonics, not yeah, if there is a signal which is of a sinusoidal signal, if you add a third harmonic component, if you add a third harmonic component, this is a harmonic component which this is a fundamental frequency component and this third harmonic component. You just try to look into that. These also, if you add this particular V of 1 and V of 3, the 3 signal, we'll be getting a signal. I'm not sure about it. Maybe I'm just when you're making out the addition of the 2 signals, how does it looks also. It is of this particular signal is going to subtract over this, right? That's why we have a steep over here, and we are adding at this particular duration. Okay. See, what I want to say that because of the harmonics, we are having a distortion in the waveforms. We are going to have the waveform distortion. We are going to have the waveform distortion also. Okay. And then the interharmonics. These are the interharmonics which are a non-integer multiple of the fundamental frequency components. These are the non-integer multiple of the fundamental frequency components. The interharmonics majorly because of the induction heating or induction arc furnace also, where there is a the load of that induction arc furnace is going to change intermittently. And also the inverters where you are going to operate with the PWM pulse width modulation scheme. In that case also we'll be having the interharmonics. Okay. Where you use the inverters? The inverters is when you are going to use an induction motor, any kind of a speed control over there, we'll be using that a power electronic device which is of a, sorry, not the okay, fine, I'm just giving about the induction motor, but it's not the way. Okay. Okay, no problem. In the case of the inverters where where the DC, where your DC is there, and then we have an inverter. This inverter is going to operate with the PWM scheme or any other modulation scheme also. It's not about the PWM scheme also. There is other schemes which are being available. Okay, when you try any kind of a load or any kind of a system also, maybe the AC loads. Okay, in that case, what we get over here, the voltage, the AC voltage, we use the filters here to eliminate also, but only very few harmonics may be eliminated. There are certain frequency components which are there in the AC side, that the harmonics which are being presented in even the PWM scheme also, it is the harmonics in the PWM scheme also, it is going to convert the frequency component with the switching frequency. With the harmonics which is going to present in the AC side of an inverter when you are going to operate in the PWM scheme is in the order of the switching frequency component, but not in the fundamental frequency, in the order of the fundamental frequency. Because of that, we will be having the interharmonics in a system. The interharmonics also will be creating a distortion in the voltage or even in the current also. It not okay. Coming back to the notching. This notching, you all have been studied in a power electronic course. The effect of the source inductance, in a converters, in a converters, right? Especially in a converters also, in a three-phase, in a single-phase, fully controlled converter with the source inductance also, and even three-phase also. Basically, what happened was there is a delay in a commutation from one of the switch to the another switch because of the source inductance. Because of that, what is going to happen here? It is there is, in order to have this particular kind of a current, if you take about a single phase fully controlled rectifier, fully controlled converter, in that case, a three-phase circuit, I'm just mentioning about in the case of a three-phase circuit, in that case, there will be some kind of a delay for every 60 degrees. In that case, what will happen is we are going to have this, I'm just take about one of the way, yeah, it is going to have some kind of a delay in the commutation. Don't think like it is because of the fifth harmonic component also. It is basically because of the commutation, the source inductance effect. Because of the source inductance, this is one of the problem, or one of the uh, uh, reason to have a notchings in the current or in the voltage waveform also. Because what is the reason and why we will be having the notches in the voltage is because once you allow the a current over here which is having of this nature, of this kind of a notchings, this is going to drop over here, the notching current also. Because of that, we'll be having the effects in the terminal voltage also. Okay, this notchings also is creating or it is distorting uh, the voltage, or distorting from the ideal sinusoidal signal also. Okay, basically the notches are due to the source inductance effect in the case of a full bridge converter also. Wherever you use a rectifier kind of a loads, in that case there is a effect of the source inductance. Because of that, there is a delay in the, or the the commutation delay will be there. Because of that, we'll be having the notches. Notches also is going to have the distortion in the ideal sine waveform. Yeah, the noise also. The noise also, the noise is when you see in the CRO, what you were when you are measuring a voltage signal or something, what we say was we will say some of the noise in the signal. They says about whenever you see that there is a noise, I mean, everyone used to say that there is a not having a proper grounding connection. When you have a proper grounding, all the noises, all the noise signals, which is going to attenuate with respect to that grounding. Because the noise, if you have a proper grounding, all the noises will get attenuated or get bypassed or passed through this low impedance, that is grounding. Okay. Okay, generally the grounding impedance, when you see the grounding impedance is very low. Okay. Okay, in that case, like it is going to pass all the noise towards to the grounding, towards to the ground also. Okay, what is the reason? What I am saying was, if you have the improper grounding in a system, if you have an improper grounding in a system, in that case, we can have, I mean, in that case, there is a noise in the voltage or in the current. If there is no proper grounding also, if there is no proper grounding, there will be a noise which is an unwanted signal which is going to cause in a voltage or in a current also. Okay, that is even like for any kind of a hardware or any kind of an experiment or any kind of a prototype which you are going to develop, they should have a proper grounding where the unwanted signals which is there, which is of unwanted in the sense like other frequency components, which is of very huge. I mean, it is unwanted signal only. It is not related to the integer. It is not related to the interharmonics, or it is not related to the notching, or it is not related to the DC offset also. Those unwanted signals are considered to be a noise that is going to die out if you have a proper grounding in a system. Okay. If you don't have a proper grounding of a system, we'll be having that the waveform distortion also. Okay. These are the 5 quantities which are creating a waveform distortion. The waveform distortion can be or will be there in the voltage as well as in the current also. Okay, it is creating the waveform distortion in both the voltage as well as the current. What is the reason, or what kind of suppose if you allowed that waveform distortion in a system, let's have this waveform distortion in a distribution system, what kind of the effect will be there? What kind of the effect will be there? One simple thing is there is a source, there is a feeder impedance, and there are some of the loads, maybe the load 1, which is of RL load. Okay, and there is one more load which is connected, a nonlinear load, a nonlinear load, a nonlinear load, nonlinear load. This, you know that if we allow these kind of the current, if you allow these current, especially these having the third harmonic current, if you allow these kind of the current in a system, obviously at this particular point at the terminal, if you say this is Vs and this is Vt, you will be seeing that the Vt is equal to Vs minus of Is, especially the nonlinear load into Zs. What my point is, the terminal voltage is also having the fundamental component as well as the fifth harmonic component also, or third harmonic component. In that case, what happened to this RL load? Then IRL becomes the Vt by the Z, which is of fundamental value. Okay, is about the I'm just given about Z only. Let us assume that. What my point is, the current which is flowing through the RL is having the fundamental voltage or the fundamental voltage by Z1. Also, the fifth harmonic voltage by the third harmonic voltage by the third harmonic impedance also. This load actually, it is the RL load, which is a passive load, and which is a non-linear, which is a linear load also, passive load, and which is a linear load also. But still, this load is going to have the fundamental as well as the third harmonic current, but this current is not required, but still it is flowing because of there is a third harmonic impedance which is going to offer, because XL is equal to omega 1 of L is a fundamental, XL3 which is going to omega 3 times of L is going to offer this third harmonic reactance also. What my point is, because of a nonlinear load, we have the other loads which are going to affect, or which is going to draw the unnecessary current or the third harmonic current which is not required also. Because of that, there is a heating loss will be there. Losses will be there. Apart from that, this guy will get this customer will get a unnecessary for this amount of the power also. For this third harmonic current also, he will be charged also. For this harmonic current. But this current is not required for this particular customer also. Okay, I have just given one of the example. There are other effects are there when you take about the induction motor, induction machine. The induction machine, if you are allowing if you are driving this induction motor, a third harmonic voltage or a fifth harmonic voltage, okay, or a seventh harmonic voltage, or even like a ninth harmonic. Generally, typically in our systems, these particular harmonic components are not going to occur. Ninth and then in some of the systems, in distribution system, ninth and third harmonics will not be there. Okay, why with this kind of the harmonics will not be there in the system third and the ninth? Why? What is the reason why the third harmonics will not be there in a typical systems? Yes.
Three-phase star connected.
Yeah, the three-phase star connected load will not be having the three-phase star connected. Are a star grounded, right? Or star connected?
Sir, isolated.
Screen not visible, sir.
Yeah, I'm not shared the screen also. I'm not shared the screen. Okay. Three-phase star connected load.
It's isolated star connected.
Isolated star connected load. Okay. Yeah. Yeah, isolated. See, one of the case like in a distribution system where we don't have the star connected only. We don't have the star connected point to a neutral also. In that case, there is no path for the triplet harmonic components of the current. So this is the reason why some of the cases where the triplet harmonics won't be there in system also. Even like when you go for the higher go for a transmission level also, in general, why in the transmission level these kind of the harmonics or the harmonics will only be occurred in the transmission level, in the sense like most of the harmonics will be trapped down in the downstream also, in the downstream in the sense like in the distribution system itself only, most of the harmonics will be trapped down. It is not transformed to the upstream also. Okay, because of that reason we are not going to deal any kind of the harmonics in the transmission side. We are going to deal the harmonics at the distribution level voltage only. And whatever the power quality issues which we have been studying in this course is the power quality issues which are been going to study in this course is which is related to the distribution system only. Okay, which are going to study in the distribution system only. Okay, we'll try to discuss this particular point in the next class. I'm just going to make out a little bit discussion on the transmission system and the distribution system. There are the devices are there, and some of you have been studying about the fax codes also, flexible AC transmission. There is a huge difference between there in the flexible AC transmission system as well as the this power quality also, power quality devices also. Okay. I'm going to stop over here. We'll meet in the next class.